Welcome back, Algebra Express. We are in Marecek 8.5, Part A. So we are going to start talking about square roots and complex numbers in this section. And so we will start talking about imaginary numbers at some point. So we are delving into imaginary numbers in this section. And it's the selected topics from like 8.1, 8.2, and 8.8, apparently, from the Marecek book. And so this first thing that they start us off with is square roots. So the way that they define a square root is C is a square root of A if C squared equals A. And then they ask, what are the square roots of 9? So basically, what equals 9, what can C be? And so the most obvious thing, I think, is like because that will give us 3 squared. But there's also another thing that we have to sort of account for. If we square something, negative 3 squared, we'll also get 9. There is this thing we have to count for, both the positive and negative 3, when we talk about a square root. And so this is what they're talking about here with this plus and minus. They're taking plus and minus root 9, which is 3. When we see the radical sign number, we're talking about a square root. We're talking about things being squared. And so for this section, I believe we're sticking just to square roots. I believe in the next section we'll get up to cube roots. But in this section, we're just talking about square roots. So if we're talking about the square root means both of the positive and negative 3. So if we take a positive 3 and square it, we're going to get 9. If we take a negative 3 and square it, we're going to get 9. When we see the radical just by itself, we're just talking about the principal square root or the positive square root only. So this is probably what I would typically say if I say square root of 9. I'm just talking about the principal square root. So we're looking at these things, and we want to simplify these things. So we see. So 144 is an even root times squared, right? And so if we're doing the square root of 144, the square root of 12. And so these that they are giving you at first are all sort of, they're going to be even roots. In a second, we will get to simplifying things that are not even roots, things that will stay under the radical and how to deal with those. But for now, you might notice that I have two things under the radical. They come out, and when they come out as 1. Here, I think they're trying to get out of a rule with part B. So with part B, I see the square root of 25 over 49. Break this thing up. 25. Break it up into its factors. Multiplying fractions, I could break them up in 2 separate fractions if I wanted to. And you might notice you have 2 of the same thing under the square root. So I have 2 of them. They're going to come out as 1. So couples get to come out 5/7. So this is the sort of long way to do it, probably. There is a sort of maybe shortcut that you could use. So if this is 5/7 and we're looking at this thing square root of 25 over 49, the sort of short way that I would probably do it is we could look at the square root of 25 over 49. The square root of 25 is 5, the square root of 49 is 7. So we can treat this thing, this radical, sort of like it is a exponent. So it is similar to an exponent. And we'll talk about that later. But we can sort of treat it like it's an exponent. Okay. So now we're thinking about this. And if I want to go look back at what my definition of a square root says, I want a c squared such that it is equal to this thing. So this would be c squared is equal to a minus 100. So I want a number that when I square it is going to equal a negative number. So you might think 10. 10 might be like something that pops into your brain. But if I do 10 squared, it would be a positive 100 if I square it. If I do a negative 10 squared, it would be positive 100. So I'm trying to think about something that's going to give me a negative number when I square it. So right now, just for a few more pages, we're going to pretend like we don't know what that is. And then we'll come back and we'll talk about that. So we want to simplify this thing. So square root of 5 being squared. There are a few ways you can think about this. This is a square root of 5. There's another way to write it. You can think about it as a square root of 5. And I have 2 5s under my radical. They come out as 1. This is also a square. This is also a square. So those are sort of inversing each other is one sort of way to look at it. But there's a little stipulation that does happen. If we have something like this, they're not exactly inversing each other, or that previous one. So if we look at this one, we have a minus 3 being squared under a radical. So we see this radical, and I want to look at this thing. I have a minus 3 times a minus 3 on the inside. So I'm just writing out the definition of what that square means. And if I have that minus 3 being squared, you might notice that that's going to become positive. I have a 2 negative. It's going to become a positive 9. And so I'm doing the square root of 9 is 3. So this comes out as a positive 3. Okay. So they want to go over some perfect squares here. So 5 squared is 25. We did that one. 6 squared is 36. 7 squared is 40. Is 81. And so I've been mentioning this approach. If we can find 2 of them under a square root, we circle 2 of them, 1, 2, and they come out of the square root as 1. So that is one sort of approach you can do. If we can circle 2 of them, they come out as 1. The other approach is if you notice it's just a perfect square root, you can take out a perfect square root. So like the square root of 25, I would be okay with you just jumping to 5. Square root of 81 is 9. If you know these things and you can use them to your advantage to simplify these radicals, then go ahead and do that. So this is powers of x now. So we're thinking about what would things look like if we could take square roots. So I'm taking square roots of this side to get over here, right? I'm going to look at this thing. So x squared is going to be x to the 2 times 2, giving me x to the 4. So radicals to radical, or exponents to exponents. I'm multiplying the exponents as the operation. X to the 3 times 2 is giving me x to the 6. X to the 4 times 2 is giving me x to the 8. And so if I take a square root of x to the 4th, it'll be an x squared. I can take a square root of x to the 6th. It'll be an x to the 3rd. So if I'm going the other way, it's sort of like I'm dividing by 2 to take a square root. So what is true of n if x to the n is a perfect square? So if we have a perfect square, we're looking at these powers over here. 2, 4, 6, 8. What do we appreciate? This exponent is even, I believe. Even or a multiple of 2 is saying the same thing. Okay, So there's an assumption that they're making that we might want to know x represents a non-negative integer. So just the same way, like we could have something weird like this happening, and maybe that x might have been negative to begin with. They're assuming my x is not negative. So we don't have to account for things happening here that might be weird. And so they want to take a square root. They want to take a square root of x squared. So x squared looks like square root of x times. Okay, and so if we have two of them, I sort of mentioned this, but we got two of them, we can bring them out as one. So this is just going to be x. This is one way you can sort of do it. There's two of those next to the fifth, but I've kind of sort of already mentioned it. If we're going to do the square root of an exponent on a variable like this, we multiplied by 2 to get to here, so we have to divide by 2 to get to here. So 2 divided by 2, I guess, is this 1. This I don't see over here, but you could have wrote out 10 x's. Put them 2 by 2, 1, 2, 5. You get 5 groups. So you'll get 5 x's coming out of there, being multiplied together. We're doing groups of 2 is one way to do it. Okay. Use a calculator to obtain the decimal approximation of the square root of 30. Ooh. Grab my calculators right here, and we do square root of 30. So this is just a sort of calculator check problem. Can you do the square root of 30 on your calculator and get something that is reasonable, like 5.477 is probably pretty good. Okay. And before we did that, if you look at where 30 is, and we go back to our perfect roots, we would expect a number between 25 and 36. We're doing 30. 30 would fall between 25 and 36. So we know the answer is going to fall between 5 and 6. So even if you don't have a calculator, you can sort of approximate these by looking at the perfect square and thinking where this falls between my perfect squares. So this falls between 25 and 36. It will fall between 5 and 6. Product property of square roots. So if a and b are real numbers, and they should really say that they are positive here. I'm not so sure this works very well if you have negative numbers. But we're not doing negative square roots until 2 more pages, I think. But if a and b are positive real numbers, then we get this thing. And so if they are separate roots, we can combine them under one root and multiply them together, is what this thing is kind of telling me. So if I have 5 and 20 under separate roots, what this thing property is giving me is that I can put them under one root and multiply them together. I'm going to do 5 times 20 under one root. So we're going to use this property. We're going to use this property this way, and we're probably also going to use the property going that way. 5 times 20 100 root of 100. So I hope you know a root of 100 is going to give me 10. Okay. Now we want to do things that are not quite so easy to simplify, or aren't going to simplify out of the radical quite as evenly. And so we have something like 45. So 45, and the best sort of approach to this is 45 is 9. simplify the root of 45, it is 3 times 3 times 5 is my prime factorization. And now's the time that we make fun of the loners. So the couple of things you come out, the singles people have to stay in. So the couple comes out. The couple comes out as a single couple. They come out as a 3. Underneath the radical, we still have 5. So if we want to do the root of 45, it is 3 square root of 5. So if you want to do it this way and group things together in groups of 2 and pull them out as 1, this is one way to do it. There is another way. So root 45, you might notice there is a root of 9 in there. If we want to use that to our advantage, we can use that to our advantage. So root 45, think about it as root of 9. Because maybe you know 9 is an even root, and you want to use that to your advantage. If they're together under square root, we can kind of look at them as being separate. And so you might notice that root 9 is 3. Just solve this 2 different ways. We got the same solution. So root 45 is 3 the square root of 5. Okay, so the next number we want to do is 48. So similarly, we want to do the prime factorization of 48. So do a tree, do the prime factorization of 48. Okay. Be dumb and pretend like I don't know what divides 48. 2 will divide it, and 2 and 6, 2 and 3. Okay, I'm looking down here. I got 2 times 2 times 2 times 2 times 3. So I'm doing the square root of 2 times 2 times 2 times 2 times 3. So the rule is couples come out. Singles have to stay in. So we have 2 times 2 coming out. And we still have a 3. You could have said this is 2 to the power of 2. That would have also been correct. But this is 4 of 3. Or 4 times the square root of 3. Okay, so I think there is an even root that maybe you could take advantage of. We took out a 4, so there'd be 16 times 3 is one way that you can break this apart. If you knew this was 16 times 3, you break this apart into separate roots of 16 times 3. We might know square root of 4. Something you're looking for in there, you can absolutely do that. And I just realized that's what the instructions ask you to do. So rewrite the expression as a product of a perfect square and a remainder. So you can do that with these. Absolutely. If you wanted to pick out perfect squares, it might help save you a little bit of time. If you want to go this way with it, I'm fine with you doing this way. Whatever way makes sense. Both ways make sense. But I would highly suggest being familiar with this way, because this way is more thorough and it will get you there. This way might not be as clear. So we want to simplify this thing. X to the third. Write out the definition of the x to the third. We got our square root of triple x there. Oh, it's a sports action-packed Vin Diesel thriller of the square root of x times x times x. So here we go. How do we do this? Couples come out as one. Have to say it again. I'm going to one time. On the inside. Okay. It was the first time we took a square root of a variable there. Okay, now I think they're going to throw probably things with variables and numbers at us at the same time. Always use the largest perfect square to factor. Okay. So they're trying to get at something here. If we have the square root of 9, you can do what? 2 and 7 will give you 9, 5 and 4 and 5 will give you 9, 6 and 3, or 8 and 1. Okay, so which of the above makes use of the largest perfect square factor? So what they're saying is to look along here at the perfect squares. So the even number exponents, so at these perfect squares, 2, 4, 8. Which one of those is the largest? This one. Okay. How can you tell that the largest perfect square factor could not be taken out? Because the next largest perfect factor would be what? X to the 10th would be over this. X to the 10th is more than the X to the 9th. We can't take out more than what we already have right here. So the largest we could go is X to the 9th, but that's not even. Try to look at the even ones. We want to take out the largest, so we want to simplify this. So X to the 8th, and I talked about this already, but if we have an exponent and we take a square root, what we're kind of doing to the exponent is dividing this thing by 2. So this is going to look like X to the 4th, and there's still going to be an X left over underneath there. And so if we have an X to the first power, it might be really obvious we can't take it out of a square root because there's only one of them. We need 2 of them to take out of a square root. And if you look along here, they don't really explicitly say this, but like the reason why we're taking out the largest, if you look along here and we look at any of these other ones, so if I'm looking at like X to the 3rd, if I look at any of these other ones, you can still simplify these out a little bit more. So this is, I guess we have like X to the 3rd, X squared, X squared, X. And so this will be X to the 3rd times X times another X will give you X to the 4th. Okay. So these are not fully simplified. We can still take more X squareds out of these things. The easy way of doing square roots is there's a sort of algorithm that is happening here. If we take 9 and we're grouping it into groups of 2, we're going to get 4 groups with our remainder. And you might notice a sort of correlation between this and our solution here. There are 4 that come out. We get 4 of the groups, and there remains 1 underneath the radical. So essentially what we're doing is dividing these things by 2. If it's an odd number like X to the 9th, we're going to get something with a remainder. If we get like X to the 8th, we're dividing this thing by 2, it's X to the 4th.
x to the 7th, which will give you what? X to the 3rd with 1 remaining underneath. So 3 times 2 plus 1
is another way to look at what you have. Okay. And from now on, that's probably what I'm going to do. I'm probably going to look at this. I'm going to divide 9 by 2 and figure out how many come out and how many are remaining. So if we look at the square root of 20, we can look at these things. These things are different. We can look at the root 20 kind of like it's different from the root 9. We can look at our constant kind of separate from our variable. So if we do that, root 20, if you can think of good even roots that would go into there, that might give you an advantage. If not, you can write out the prime factorization. But I think I'm going to jump to the root 4 and 5. Okay. Times and divide 9 by 2, I'm going to get 4 with the remainder of 1. And so I kind of said it, but if we're, well, I didn't say this explicitly, but if we're dividing by 2, you might notice we're going to get a remainder under here. So anytime you get a remainder or a remaining x variable, it really shouldn't be any power larger than 1 because you shouldn't get a remainder larger than 1 if you're dividing by 2. Okay, so we need to simplify this maybe a little bit. Root 4 is going to be 2. I have an x to the 4th that's also on the outside. What I have left on the inside is a 5 and an x. And a horribly drawn radical side. Okay. 1 down, 3 more to go. So root 80, x to the 11th. So I want to look at that root 80. And 80 is probably a pretty large number. I probably don't want to do any tricks with this. I probably want to do this. So 80, it's like, oh, if I don't know anything else, I can always do 2. Trying by 2 a lot of times we'll get it really down pretty low. And this is 2 times 2 times 2 times 2 times 5. I'm looking along here. I'm looking at groups of 2. 2 comes out twice. 2 times 2. 5. So root 80 is 4 root 5. And then I still have to worry about that radical of x to the 11th. So that thing is still there. I know I didn't talk about it quite yet. On the outside, now when I think about this, I'm dividing this thing by the power of 2. So 11 divided by 2 is going to give me 5 with the remainder of 1. So I have 5 of them that are going to come out. I'm going to have 1 underneath the radical still. Okay. And there's one other thing I've got to bring down. There's still 5 in the radical. So 5 times 2 will give me 10, plus another 1 will give me that 11. we want to look at 64x to the 7th. So right away I'm looking at 64. That looks like an even square root. Nice. We have a root 64 is 8. We're doing x to the 7th. We divide 7 by 2. The remainder of 1. On the outside, the remainder of 1 on the inside. If I go back and look at my even roots. So if you want to go back and look at the first page where you wrote all those even roots, 50 is divisible by one of those even roots. It is divisible by 25. So if we do 25 and 2, that will give us about the root of x to the 5th. So this thing looks like 5, and this is a radical 2. This thing is going to look like this is even. So I would go x to the 6th divided by 2 is going to give me 3. So I'm getting 3 x's coming out of the radical. I'm going to have no more x's underneath the radical. So I might want to clean this up a little bit with things outside, and things by himself. There we go. 5x to the 3rd, the square root of 2. Now we want to talk about imaginary numbers. So now we're going a little bit of a different direction. Well, same direction. It's extending it a little bit. So we want to talk about something a little bit different, a little bit weird. And we talked about this thing earlier. What happens if I do like the square root of a minus 100? So I want to go maybe something a little bit easier. What happens if I want to go to the square root of something like a minus 1? And referring back to our definition, that would be where my is equal to a negative 1. So I want something that when I square it, it will give me a negative number back. And so we don't know anything like this before because previously it was either both positive, and if they're both positive, my solution would be positive, or they were both negative numbers, in which my solution was going to be negative. So going back to every number that we know of, if it was positive and you square it, it's going to give you positive. If it's negative and you square it, it's going to give you negative. So we've never encountered anything like this. And so they don't call it c squared, they're going to call it I squared. So I squared is that such number. So this is the imaginary number that we're introducing. So the imaginary number is the such number that when you square it, it is a minus 1. Another way to say that is that I is equal to a radical minus 1. Or I is the square root of a negative 1. Okay, and so they give us a few radicals to simplify now. Okay, so they give us a few terms to simplify. My sort of suggestion is to go for the i's first. Pluck out the i's first. Do that, the first thing that you can do. And so looking at what I mean, if there's a negative there, I can think of this as being the square root of like a minus 1 times 4. And so I always want to pick out that negative thing first. So always look at the negative, pick it out. Look at the 4. So this thing is over here. Square root of minus 1 is giving me an I square root of 4 is giving me 2. I'm not usually going to write I2. I'm going to be writing 5. Similar with what's happening here, I want to do a square root of a minus 5 now. And we're looking at this thing like a minus 1 times a 5 in the square root. This is like the square root of minus 1 times a square root of 5. So this thing is an I, and I have a root 5. And so I want to get those negatives, and I want to get those negatives out. And that's it. If I'm set up with the order of operations, like that should be the first thing that I kind of go for. Go for the i's first. Plug out the minds. And then deal with the rest. But we want to now do square root of a minus 100. So same thing. I see a minus 100. 1 times 100. I'm going to pick out that I. Negative 1 is an I. This is times 100 is going to give me 10. This is going to give me 10 i's. Okay. We are talking about imaginary numbers, just things that are pure imaginary right now. Simplifying and express in terms of I, radical negative 48. So I think we might have done this one before. It was one of the previous ones. The radical 48 from the previous page. So if you want to do a lot of extra work and figure out what the factor of 48 is, you can do that. But 48, so what I'm doing is I'm tacking an I onto this thing, basically. So radical minus times radical of 48 is what this breaks into. And so this is an I, so I'm going to have 4I radical 3. So hopefully we can look back and save ourselves a little bit of work if we did the same work previously. So the I is going on the outside when we take it out. We're plucking the I out of the square root. It is coming out. It is staying on the outside. So I will always write my I in front of my radical right here. Sometimes your book will put the I over here, and I really don't like that, because if you extend your radical too far and you put your I underneath the radical, it does change it. They're different things. I don't want to really go into too much of that, but they're not the same thing. And so I would keep it on the side of it typically. And so maybe a little lesson in why I say pluck out the I's first. Are we doing? Yeah. Okay. So if we're looking at this thing and we pluck out the I's first, root of a negative 25 is going to give me 5I. Root of a minus 4 is going to give me 2 and an I. And so if I'm multiplying these things, and I pluck out my I's first, I'm going to get like something like 10 I squared. And we're about to do this a lot in the next step, but I never really want to write anything over a single power of I. So if I have an I squared, this is anything as a negative 1. And so this would be a negative 10 if we solve it the correct way. If you don't solve it the correct way, if you don't pull out your I's first, what might you do? So I'm going to do this in maybe a different color. I'm going to do this. It's red. This is caution. Times the minus 2. So I got 2 negatives. Apply together. Positive. The positive thing out of this, and it's not going to come out with the correct sign. So again, pluck out the I's. This is the moral of the story. And it should be like takes a certain kind of priority to get those I's out of the radical. Should be first priority. Okay, complex numbers. So we talked about imaginaries. These were imaginaries. These were pure imaginaries. They just had a imaginary and some sort of coefficient on it, like a 2i or a 3i or a few radicals, 4 radical 3 or 4i radical 3. So now we want to talk about things that look like a plus bi. And I think it says A and B are real numbers. So these things are referred to as complex numbers. So if we're thinking along here, we have the set of complex numbers that look like A plus BI. Okay. And so if we want to express imaginary numbers with complex numbers,
Are we able to do that? Complex.
if I want to express those pure imaginary numbers like I was doing up here,
Things that look like 4i or 3i.
or radical 4i, things that look like some multiple plus I, what you might notice is I don't see an A. So if A is equal to 0, I can get things like this, like 4i and 3i. Okay. The other thing I can get with a complex number is I'm looking along here and I can let A be equal to 0. The other thing I could let be equal to 0 is my B. So if my B is equal to 0, then I just have things that look like A. It may not be super obvious, but I can express any real number with a complex number. All it means is that the imaginary coefficient was 0. So the imaginary component was 0. It wasn't there. So complex numbers, I can express pure imaginary. I can express any real number out there. 3, 4, pi, give it to me. I can express it with this. Any number that doesn't have an imaginary component, I can express it. Any number that's pure imaginary, and any that's like a mixture of the two. So like 3 plus 2i, pi plus root 2i. I can put crazy any real number in those places. It can have like a mixture of both real and imaginary components. And so complex numbers, we can express all the imaginary numbers, we can express all the pure imaginary numbers, we can express all the real numbers, we can express any sort of number that we know of out there at this point, I believe. It might be every number I know of out there at this point. It's from the typical number set. Okay. So they give us some examples, and this is what they're talking about here.
Like our A is equal to 2, our B.
So this is A plus BI is what I'm looking for.
A plus BI.
Sort of form it's in.
So I'm looking for A plus BI here. I'm looking for A plus BI here.
And so this is what I was going through. It can have both imaginary and regular real numbers. It could have pure imaginary, which means my A would have been the number 0 because we don't see it there. It's like 0 plus 7i. So this is my A is 0, my B would be 7. My B would be 0. And so a little bit about how we treat I. We treat it just sort of like an X, just sort of like any other variable out there. So it is a weird guy, but he gets treated just like everyone else. So 1 plus 2i plus 3 minus 5i. So I'm not going to spend maybe too much time doing this one, but we're doing 1 plus 3 is going to give me 4. 2 minus 5 is going to give me minus 3. If you have to draw an X to get there, draw your X for a second and then erase it in the end. 1 plus 3, 2 minus 5. I'll probably do a little bit of distribution. The like terms, that's the word I'm looking for. I got to make sure I add the like terms of 3 and minus 8. 3 minus 8 minus 5. 2i plus 3i is going to give me a plus 5. So it's just like you work with any other variable. You treat it just like any other variable. Like I said, if you have to write an X instead of an I, and then switch it back in the end, that might be something that helps you. You can go for that. It's the same thing. It's a variable. Okay. So we are almost on the last page. Last page now. So we added, subtracted. We did it just like it was a normal variable. We're going to multiply. And guess what? We're going to treat it just like it's a normal variable. And then we're going to do maybe a little bit extra work. But for the most part, we're going to treat it just like we distributed things previously. So I'm going to do this 3 times 2 is 6. 3 times 9 is going to be 2 lots. 7 and then I is 5i2. I plus 5 is 9. They're going to be plus 45. I'm doing I times I. So this is I squared. So we do this step just like we've done before, just like any other variable. We're going to distribute this thing. We're going to add like terms. 6 plus what? 37 i's plus 45. And there's one thing I want to do now. So I don't have to write an extra step, basically. But there's one thing I want to do now. This is a 45. This is an I squared. I really don't ever want to write anything over a single power of I. So if I see an I squared is equal to a minus 1. We want the thing that when we square it, it's going to be a minus 1. So I got to do a little bit of crunching because this is 6. So now this is going to be 6. This should be minus 39 plus 37. And I'm looking at my solution just to kind of double check things. I want to make sure things are A plus. I skipped over that on the previous problems. But on my previous problems, I also want to make sure that my final format is in the A plus BI form. So I'm going to start with the real component, and I'm going to end with my imaginary component, basically. A plus BI form, but these were in. So I do want to make sure my solution is in complex form. Okay. We've got a few more multiplying activities. So these are student activities. So you should be attempting these on your own. So something you might notice before you do these, it might give you a little insight into what you're doing, is these might look a little bit like we had with conjugates maybe before. This thing, and I yelled it at you, you better not try to do a distribution with exponents. You better write that thing out, right? Write it out twice. If you try to do distribution with exponents, I can almost guarantee you're going to miss like that middle term that's in there. It doesn't just come out without writing it twice. But this looks like 3 minus 2i. 3 plus 2i. We have done something similar to this, just not with i's. We've done it with x's. 3 times 3 is going to give me 9. I'm going to do 3 plus 2i. I'm going to give me plus 6i. 3 minus 2i into 3 is going to give me minus 6i. And I have a minus 2 times 2 is going to give me 4. I times I is going to give me I squared. So I'm looking at this thing. I have a 9. And you might notice, you might look inside it here and look at plus 6i minus 6i. So these are going to add to 0. So these are going to add to 0. They're going to simplify. I really don't need to account for those anymore. But I still have a minus I squared. So those are adding up to nothing. have my minus 4i squared.
And we said it previously, we don't want any I that is over the power of 1.
It is an I squared. I can make a substitution here. I can plug in minus 1.
So instead of 9 minus 4 times the minus 1, this is going to be like 9 plus 4.
You give me 13. 13? With all that? So we start off with something like this. And like I said, they look like conjugates. So we do the conjugates. You might notice the middle term with the i's is going to simplify out. The other term is going to have an I squared on it. We're going to end up with something that is a pure real number right here. So if you want to get rid of your imaginaries, they're trying to set you up with this knowledge. If you want to get rid of imaginaries, you can multiply conjugates together, and it will get rid of the imaginary component. Okay. 4 plus 3i. Let's do this, guy. And I said it already, but if you're not doing this, I'm disappointed in you. 4 plus 3i. And 4 plus 3i. Better write it out twice. That's what I'm talking about. Do it. 4 times 4 gives me 16. Plus 12i plus 12i. And then the last thing is plus 9i squared. Okay, so I got to combine a few like terms. 16 plus 4i will combine. This is plus 9i squared plus 9. I don't want to write my I squared, I want to write a minus 1. So 16, this is going to become minus 9 plus 16 minus 9 is 7 plus 24i. And I wrote it so that things were in the a plus bi form. Okay. And so what do you notice about a perfect square? Probably not anything too pretty. I'm not really too sure. Maybe 7 is what, 4 and 3. I think that might be true. I'm not sure. There's not really a straightforward pattern of this one. That I can see. And so we did those two. We did the conjugate. We did the 4 plus 3i. What product from the previous question is a product of complex conjugates? It's right there. 3 minus 2i. 3 plus 2i is what you're talking about. And so how do conjugates differ? They differ by one sign. Typically, we swap the middle sign. From one is plus, one is minus. What kind of number did we end up with? So we ended up with the number 13. It was a real number. It didn't have any imaginary parts, so it definitely wasn't pure imaginary. It wasn't a complex that had imaginary parts. It was just a pure real number. So if we do this, what sort of numbers should we end up with? We should end up with, hopefully, a pure real number. Should not be any i's left over. So let's see if that's the case. This looks like a conjugate. They're giving us one last problem. Plus 3i. And maybe I'll write everything out just to be super annoying. And so everyone sees it. So root 2 times root 2 is the first thing that I'm doing. I'm going to do a minus 3i root 2. And I'm going to get a plus 3i root 2. The last thing is a minus 9i squared. Root 2 times root 2, I didn't do it, but you have the same thing multiplying itself underneath the square root. That is 2. this thing right here in the middle.
Right there.
Those simplify, choose 0. Those are the same thing. One of them is adding, one of them is subtracting. It is no more.
I have a minus 9i squared. That's like a minus 9 instead of I squared. I really think about this
As a minus 1.
So this looks like 2 plus 9.
So this looks like 11. So we expected to get a pure real number. We got a pure real number, number 11. Okay. And so you might notice we got rid of the I. We also got rid of that square root by doing the conjugate. So we've got number 11. All right. Take care. See you next time.